In this video, we're going to focus simply on the bonding aspect of the attractions that occur within particles and between particles. So bonding, if we remember correctly, there's 4 different types of bonding that we discussed in the previous video. Ionic bonding, covalent bonding, many times called molecular bonding, metallic bonding, and network covalent bonding. So first of all, let's make sure we distinguish between those two again. Okay, anytime you have a bond, bonds are always significantly stronger than those intermolecular forces. We mentioned those in the previous video. The hydrogen bonding, dipole-dipole London dispersion, those much weaker than an actual bond. So bonds are significantly stronger than intermolecular forces. Okay, so bonds are significantly stronger, okay? And obviously in a bond, the atoms are much closer together than in an intermolecular attraction as well. So the first type of bonding that we're going to discuss is called ionic bonding. In an ionic bond, you have ions, and ions typically form between a Na plus and a Cl minus, or an Mg2 plus and a Cl minus. I should use Cl minus every time. Or O2 minus, or Al3 plus and SO4 2 minus. Positive charges and negative charges, always in ionic bonds. Okay, in an ionic bond, the electrons transfer from one atom, the metal, to the non-metal. Okay, that's why the positive charges and the negative charges. Okay, because the metals lose electrons, the non-metal portion gains the electrons. Okay, so obviously they're called ions. The metals lose, the non-metals gain. And again, since the electrostatic charges are large, the bond is a strong one. And since Coulomb's law predicts that the force increases with increasing charge, the strongest ionic bonds are formed between ions that are small, because again, the distance between them is very small, and that have the highest charges, that have a +2 or a +3 charge versus a -1 or +1. So some of the things that you should remember about ionic bonds, or should know about ionic bonds, is first of all, they have very high melting and boiling points. Okay, and so it takes a lot of heat to melt an ionic solid, and it takes way even more heat to actually turn a liquid into a gas of something that is an ionic compound. And therefore they have what's called very low vapor pressures. A vapor pressure is how much pressure is formed when that liquid does turn into a gas compared to, say, a molecular compound or something like that. Okay, another thing that you need to know is that ionic compounds do not conduct electricity when they're in the solid form. Okay, the ions are held rigidly together, so the electrons can't move around. But if you melt them, so when melted, so in the molten form, or if you put them into water, then they do conduct electricity. You need to know all of those things about ionic compounds. So they're made up between positive and negative charges, typically metals and nonmetals. They have very high melting and boiling points. They don't conduct electricity when they're in the solid form, but they do when you melt them or you dissolve them in a solution. Again, those are kind of those random things that if you remember them, that's great, because you're likely to see a question about that. Okay, another thing about ionic compounds is they're held together in a very large, this thing right here is called a lattice structure. Okay, in a lattice structure, you can see this is partially why they have such high melting and boiling points. Is this chlorine, for example, right here, is surrounded not by one sodium, but by 1, 2, 3, 4, and if there's another one on top, 5, there could be another one on this side, 6. So the positive charges are surrounded by a whole bunch of negative charges, and the negative charges are surrounded by a whole bunch of positive charges. And what that does is it gives ionic compounds very flat sides. If you look at salt under a microscope, salt has very flat edges like a cube, whereas if you look at sugar, which is not an ionic compound, it's very jagged. Its edges are very jagged compared to an ionic compound. Okay, so electrons are transferred. It's a lattice structure, high melting and boiling points. They don't conduct electricity as a solid, but do when you melt them or when you dissolve them in water. Okay, covalent compounds or covalent bonding, oftentimes called molecular compounds or molecular compounds. They don't transfer electrons, they share electrons. Okay, when we draw, for if you remember Lewis electron dot diagrams, okay, we draw those, and when we draw those bonds, the lines between like an H and an O in water, okay, that is a covalent bond, and those electrons, this counts as each line counts as 2 electrons, one from one atom, one from the other. So those 2 electrons are being shared between the hydrogen and the oxygen. Okay, that is a covalent bond. And how do you know that? Because again, it's 2 non-metal, 2 or more non-metal atoms put together. Okay, so non-metals only, they share electrons. There can be double, single, triple bonds. We'll talk about those later on. Some important things you also need to know. How are they different from ionic compounds? They don't conduct electricity at all. Okay, molecular compounds do not conduct electricity, whether it's liquid, solid, whatever. And they do have, and I'm not sure if this is in here, but compared to ionic compounds, they have very low melting and boiling points. Okay, so you can kind of see a representation of that here, where there's an attraction and a repulsion at the same time. Okay, metallic bonding is just some metal. When you have a sheet of metal, when you have the copper wire running through your house to run the electricity, those are all held together by metallic bonding. Okay, and some of the things that you need to recognize here is that the electrons in metallic bonding are delocalized, which means they can move. Okay, another way that a lot of times they talk about, they call that a sea of electrons, and you can kind of see that down here, where the purple or the blue dots here basically can move around. So when you turn on the switch and a whole bunch of electrons start moving in from this side and start moving in that direction, what happens is all the electrons start moving. Okay, and the movement of electrons is electricity. Okay, and that's why metals are so good at conducting electricity. Much again, remember, covalent compounds don't at all, and ionic ones don't when you're in the solid form. So they do conduct electricity. That's a big difference there. Metallic bonding does conduct electricity. They're great conductors of heat as well. Again, the metals are malleable, which means they can be bent and shaped without breaking. And they are ductile, which means they can be made into wires. And why is that? Because of the delocalized electrons. Okay? Those atoms can slide, they can roll, they can move over each other without breaking that metallic bond, because the electrons are able to move around from one atom to another. So this is a real AP question here. A student claims that gold is malleable because it is dense. Do you agree or disagree with this claim? Well, it is true that gold is malleable. Okay, but is it because it's dense? Did we just mention density at all? Of course not, we didn't. So of course we're going to disagree with that claim. And why? Now we're going to justify that. Why are we disagreeing? Well, gold is malleable because, why? What did we say just up here? Because metallic bonding has delocalized electrons, allowing the metal to change shape due to the movement of the electrons. Okay, or you wouldn't even have to say that. Okay, just simply because disagree because metallic bonding has delocalized electrons, which allows the metal to change shape. Or just, you don't even have to say that. You can say which makes it malleable, which again makes it to change shape. Okay, so here's those first 3 types of bonds here. Again, notice the energy. The energy can vary quite a bit, but the ionic and metallic are higher in energy than covalent are normally. Okay, you've got a positive charge, negative charge here. You've got your sharing electrons in covalent. You've got delocalized in metallic. Okay, lots of, again, kind of random little tidbits of information there to remember about that. All right, our last type of bonding that we're going to discuss, so we've got ionic, covalent or molecular, and metallic. The last type we're going to talk about are what are called network covalent bonds, okay? Again, some of the little details you should know about network covalent bonds is they're much, much stronger than covalent and ionic bonds. So therefore, they have the highest melting points out of all of them, okay? And they do not conduct electricity. We'll talk about that in just a second, but in general, they do not conduct electricity. So some of the things that use network covalent bonding, there's not much. Okay, carbon actually does when it bonds with itself, which has a bond with itself. Okay, a diamond, like in jewelry, or even graphite. We always call it lead, but it's actually graphite that's in pencils, whether it's mechanical or a regular pencil. Those are made of graphite. Okay, and that's different forms of carbon that are, again, network covalently bonded to each other. Okay, and so you can see here, they're bonded to one another in a very strong, they are covalent bonds because they're nonmetals, but again, they're very rigid, they're a fixed covalent bond, they have super high melting and boiling points, okay? Whereas with graphite, this is the network covalent bond right here. You're like, well, wait a minute, how can that be such a strong bond? I just have to put my pencil on my paper and it writes, it breaks off, okay? The reason is because there's layers, okay? There's a layer of graphite here, there's a layer of graphite here. What's holding those layers together is a very, very weak intermolecular attraction, okay? And so writing with graphite or using it as like a lubricant in, like with ball bearings or things like that, graphite's used a lot, like Pinewood Derby cars, things like that. Because again, they have very, very weak intermolecular forces holding them together. So the covalent bonds within the layer are strong. Okay, that network covalent bond here between the carbons very, very strong. It's just that weak attraction between those layers that is weak. Okay, and that's what those dotted lines here represent. Okay, so they slide over each other really, really easy. It makes graphite very, very soft and a good lubricant for things like ball bearings, things like that. Okay, so one form of network covalent bonding is carbon in terms of diamond, in terms of graphite. Another one is sand. Okay, sand, which is silicon dioxide, used a lot in computer chips, used a lot in like the electric vehicle industry. They use silicon a lot because it does create this network covalent solid. Okay, and again, it is what's called a semiconductor, which means silicon sort of conduct electricity, okay, but in general, it is a poor conductor of electricity. Okay, one of the ways that you can improve the conductivity of silicon, which is what they do to it to make it conduct electricity better, is to take some of those silicon atoms out and replace them with an atom that has more valence electrons. Okay, this is called doping. It has nothing to do with drugs. Don't get excited. Okay, doping an element is basically removing some of those atoms and putting a different element in there that, again, doesn't have the same number of valence electrons, has more valence electrons. So in terms of silicon, an element that you could dope it with pretty easily would be right to the right of it, phosphorus. Okay, phosphorus would be a great element to dope it with because phosphorus has 5 valence electrons where silicon only has 3. Okay, so here's the type of questions that can be a bit challenging. Okay, which of the following could be the identity of a white crystalline solid that exhibits the following properties? Melts at 320, doesn't really tell us much. It does not conduct electricity as a solid. Okay, so that means it's not metallic. Okay, but it does conduct electricity in aqueous solution. Oh, so it does conduct electricity when you put it into water. That has to be ionic. So which of those 4 there is ionic? Sodium hydroxide, metal, non-metal. Okay, A is covalent, C is network covalent, the silicon one we just discussed, and D would be metallic. Okay, which of the following would be most useful in providing if the substance is an ionic compound? So which of these is going to help us figure out whether it's ionic or not? Looking at the crystals under a microscope, we sort of talked about that because the ionic ones tend to be flat. Determining the density of the substance. We didn't really talk about which one's more dense or not. C, testing the electrical conductivity of the crystals. The problem is ionic and covalent both do not conduct electricity as a solid, so that really wouldn't help us. Testing the electrical conductivity of an aqueous solution, though, basically the same answer as before. That's going to tell you whether it's ionic or not. Okay, number 3. Again, somewhat similar. The melting points don't help a ton because even here, it's a low melting point. That must be covalent. Well, but then it also tells you the electrical conductivity in the solid phase is high, and in the liquid phase, it's also high. So what's the only one that conducts electricity as a solid and as a liquid is metallic. So Y has to be metallic. So again, the melting point numbers don't really help us much at all. So substance Y has to be metallic. Well, right away, boom, you're done. Because what's the only one that has substance Y as metallic is D. Okay. Now, your other choices, let's just kind of go through Z. How do we know what Z is? It doesn't conduct electricity as a solid, but it does when it's in the liquid form. That again is ionic, so that has to be Z. And then X could be covalent or it could be network covalent. But notice that covalent is not one of our choices. And the super duper high melting point kind of gives it away that it's a network covalent one, and it doesn't conduct electricity at all. So X has to be network covalent. All right, a couple more here. So this compound did not conduct electricity as solid, but became conductive when dissolved in water. So hopefully you're starting to see they're kind of a pattern. They kind of do the same types of questions. Okay, what type of interactions occurs between the particles in the substance? So it's highly conductive when dissolved in water. That is ionic bonds. Which of the following most likely describes the solid represented in the diagram above? So you see a positive charge and you see negative charges, and they're all surrounded by each other. Again, that's got to be ionic bonding. So which of these best describes basically ionic bonding? Okay. It's soft and a poor thermal and electrical conductor. That would be covalent. It has a low melting point and is a poor thermal and electrical conductor as a solid. Again, covalent. It is a brittle, water-soluble electrolyte. We haven't talked about that term, but we will. Okay, that is also a poor thermal and electrical conductor as a solid. That's a little bit better. Okay, malleable and an excellent thermal electrical conductor as a solid. Again, we know that is metallic. Okay, so we know it's not A, we know it's not B, it's not C. We haven't learned about the term electrolyte yet, but we will here shortly. But the correct answer is C. Okay, and then our last one, N2 reacts with pure metal X to form X3N. So we've got a metal and a non-metal. The student claims that the bonds in X3N are non-polar covalent. Forget about non-polar, we haven't learned that term yet. Do you agree or disagree with the student's hypothesis? Absolutely, I disagree. Okay, and why? Because they say it's covalent, and covalent is all non-metals. And this contains a metal. It tells you a metal with a non-metal. It has to be ionic.